Perfect. Thanks so much. And yeah, I just wanted to say thank you to the organizers. Like this has been a tremendous workshop. Very grateful to be able to attend and also for the opportunity to speak. So yeah, so I'm going to talk about something more on the kind of non-perturbative QFT side of the conference and less on the confinement. And so I just want to try to understand how a lot of recent kind of conceptual understanding regarding how quantum systems thermalize and how kind of the signatures of chaos that have been typically explored in kind of many body spin systems or holographic systems, kind of how we can see these in more general quantum field theories. So I'm going to talk about work that's based in collaboration with many great collaborators. So a lot of what I'm going to show you is based on a couple papers from a few years ago, done with Luca, Liam, that I talked earlier this week, and Ami. And then also some kind of follow-up work in progress with those same collaborators, as well as Tara Farnsworth, who's in the audience, and Giorgio Frangi, who's an excellent postdoc, excellent PhD student at University of Edinburgh, who will be applying for postdocs this fall. So so yeah, so the setup, the kind of way I'm going to try to think about quantum field theory is in this kind of modern picture is thinking about a general quantum field theory as an RG flow between kind of two fixed points. And so the basic idea is that at high energies, I have some fixed points. I'm going to assume kind of for simplicity, or in this specific example, I'm going to consider it's going to be a conformal field theory, where I can say a lot about the kind of UV behavior. Then I deform it by one or more relevant parameters. Those have, some associated kind of mass scales with them. And then that triggers an RG flow leading down to the kind of IR physics. And eventually we reach low energy, which is going to be a fixed point asymptotic. And so the kind of question I want to ask today is specifically kind of what happens up here. So what happens if I look at eigenstates with energies that are much, much larger than the kind of mass scales associated with the deformation of my CFT? And so the kind of features that I want to ask about those things is, first, I just want to ask about their spectrum. So which is the spectrum of high energy eigenvalues? I can ask questions about kind of dynamics. So I can compute correlation functions of, say, operators, I can compute various correlation functions, as well as kind of expectation values of operators in these high energy states. And please interrupt if stuff is unclear or you guys have any questions. So since it's early on a Saturday, let's just give away all the punchlines of the talk at the very beginning. And so mostly what we're going to do is we're just going to see a lot of kind of intuitive expectations realized in a very concrete example. And so the first thing we're going to see is just kind of confirmation that quantum field theories are generically chaotic. So unless I have some sort of special symmetry ensuring that the system is integrable, I expect to find that quantum field theories are chaotic. I'm going to show you a generic quantum field theory, and we're going to see this. For me, at least, kind of the main takeaway that was surprising a few years ago when I first started this is that I would have thought looking at high energy states is going to be kind of trivial. Because what did I do? I took a conformal field theory, I deformed by relevant operators. And so my expectation is if I go to energy scales that are very high compared to the scales of those deformations, that I just get back to my CFT. So all my theories should be just weakly coupled. My relevant interactions should be not important. And so all of my UV states should just kind of match the conformal field theory. And this is not true. This is like as not true as it could possibly be. And so what you instead find is that if you ask macroscopic questions, so correlation functions of operators in the background of general states or things like this, then you will find that macroscopic features match that of the conformal field theory. So they look weakly coupled, and I can understand them via perturbation theory. But if I ask any microscopic questions, so what's the distribution of eigenvalues, or what's the composition of an eigenstate in terms of the original kind of CFT language, I'll find that those things are highly sensitive to the deformation and are very strongly coupled. And so the kind of intuition I'm going to have that's going to be guiding me in trying to understand these high energy states is that they're kind of governed by two broad principles. So the first is the so-called eigenstate thermalization hypothesis. This is the statement that if I look at in the background of some high energy state and I ask kind of simple enough questions like correlation functions of local operators or things like this, these high energy states are going to mimic a thermal band with the temperature set by the energy density of those states. And then also they're going to be governed by random matrix theory. So the statement is that if I look at, say, the distribution of eigenvalues, for example, in like some band of energies at high energies, then that distribution will be equivalent to just that of a random matrix. Now, of course, the full set of eigenvalues look very far from a random matrix. They're, eigenvalues of a, local quantum field theory, but if I ask kind of coarse grain, yeah, go ahead.
Space, right? Or
Yeah, I'm gonna be working in, in That's right, yeah. Yes, yeah. And then lastly, so these kind of first four statements are things that probably should just kind of expect or are kind of guiding intuition. One kind of surprising thing that we found is, at least in this very specific example, we found some states at weak coupling near multi-particle thresholds that appear at least to violate eigenstate thermalization hypothesis. These are so-called quantum many-body star states, or just stars. And so I'll tell you a little bit about this as we go on, and that's kind of the main thing we're trying to do to understand now is the extent to which these states really violate ETH or not. Yes, absolutely.
There exists, we say, like a measure zero set of states that actually are described by
Good, yeah, so yes, absolutely. So the question was if there's like some set of measure zero states that are governed by EFT or that are weakly coupled at high energies. So to what extent is this is this statement true or not? So yeah, absolutely there's a measure zero set of states. Here's a very concrete example. Take two particles, take an asymptotic state of two particles that are very, very far apart, but with some large relative energy. That is a state that's weakly coupled. So 2 to 2 scattering, like I'm not contradicting anything that you know, like 2 to 2 scattering is still weakly coupled at high energies. I can still describe this perturbative. But a two particle state with very large energy between these two guys is a set of measure zero states in the full spectrum of kind of high energy eigenstates. So if I just ask, here's a random, eigenstate at high energies, he's going to be some very strongly coupled dense spectrum of like many particles.
but in your example, this particle scattering also would be in some in the tree, because you have kind of if the exchange is small, right, it would be fully so powerful. I mean,
So good. So yeah, so if I'm understanding your question correctly, yes, if I ask for an inclusive question of like two particles scattering to anything at high energies, that's going to be strong coupling. But if I project onto the very specific final state of that I only want to ask about 2 to 2, then that'll be weakly coupled. If that's, if I'm understanding. Yeah, absolutely. Okay, great. So this is what we're going to cover. So the specific model I'm going to be considering is 1 + 1 dimensional 5^4 theory. The method I'm going to be using is a flavor of Hamiltonian truncation known as conformal truncation. My goal is to say as little about this as possible, and since I have such limited time, and really just focus on the results, but I'm very happy to answer questions afterwards. Then we're just going to kind of see various signatures of thermalization and chaos in this very specific example. And then finally, I'm going to talk about these so-called ETH violating scar states that we appear to see at red weak coupling. Okay, so here's the setting. So 1 + 1d 5^4 theory. The Lagrangian is a very familiar one where I've set all order 1 numbers to 1. And so this theory has a Z2 symmetry, phi goes to -5. And so if I look at the spectrum as I vary the coupling, or really the dimensionless ratio between G and M squared, then what I find is that in weak coupling, I just have a theory that's very close to 3 theory. And then if I look at the gap of this system, as I increase the coupling, eventually the gap closes, and I move from a Z2 symmetric phase to a Z2 broken phase. And the critical point, the point at which I transition between these two guys, is in the same universality class as the 2D Ising model. And so kind of very roughly, the kind of phase diagram, if I look at, say, energy or temperature or whatever, versus coupling, that I have this kind of gap phase to the left, I enter another gap phase to the right, and then kind of in the middle, I have this kind of Ising model, so-called quantum critical fan, or just this region that's described by the Ising model. And so what I'm interested in studying is I'm going to stay to kind of the left part of this plot. So I'm going to stay in the symmetric phase. And then I have this kind of rough dividing line between kind of IR and UV physics. And this is just roughly set by the scale of the coupling. So really, I guess this should be a line and not horizontal. But I'm going to be looking at high energy states. And I'm interested in kind of this regime up here, which I have very, very generously called a sort of quark-gluon plasma type phase, where I just have a very dense plasma of scalar particles in rank. Okay, so the method I'm going to be using is this Hamiltonian truncation. There are many different kind of implementations of this method, but the steps are all universal and very simple. So basically the idea is I want to diagonalize the Hamiltonian. I'm not sufficiently powerful because it's infinitely dimensional. So I'm gonna just approximate it by truncating. So basically, there are 3 steps. First, to put it on a computer, I need my Hilbert space discretized in some way. The kind of simplest, most common way to do this is to go to finite volume. We're gonna do a slightly different choice, but the effect is gonna be roughly the same as putting the system in finite volume. So that we get a discrete Hilbert space. Then we truncate to some finite dimensional subspace. So I keep some part of the Hilbert space that I think is going to be close to the states that I want to study, and I throw away everybody else. So then I have this infinite dimensional matrix, which is my Hamiltonian, and I just keep some finite dimensional part of it. Then I just pretend that this finite dimensional matrix H trunc is my Hamiltonian. I diagonalize it, and I look at the eigenstates. And so the kind of general way of doing this is I split up the Hamiltonian into 2 pieces. An H naught, which is some solvable theory. In this case, it's going to be just a free massless scalar. And then our potential V, which I want to stress, even though this looks like page 1 of a lecture on perturbation theory, I'm not assuming that V is some small perturbation. The only reason I'm splitting it up in this way is because I need some solvable theory so that I can evaluate the individual matrix elements of this Hamiltonian. If I didn't have some solvable starting point, like a free theory or something like that, I wouldn't know how to evaluate the entries in this Hamiltonian. But once I evaluate them, I forget all about H naught. I just have some matrix, I diagonalize it numerically. And so just to kind of stress, because a thing that I think people often are confused about is that even though this kind of looks like it might be perturbative, it's kind of the opposite of perturbation theory. Perturbation theory resums the contribution of all intermediate states to some finite order in the coupling. What I'm doing is the exact opposite. I'm keeping a finite number of intermediate states in my kind of perturbative expansion, but I'm evaluating their contribution to all orders in the coupling by numerically diagonalizing the Hamiltonian. Okay, so the flavor I'm going to be considering is so-called conformal truncation. So we're interested in studying phi to the 4th theory. So my H naughts, because of the conformal in this title, is going to be just a free massless scalar, the CFT. And then my deformation is going to be the mass term and the phi to the 4th term. So my basis that I'm going to be using is I'm just going to be using Fock space states, the kind of just free theory basis here, integrated against just basically wave functions in momentum space. The particular choice of wave functions that I've chosen are polynomials in momenta. This is because these just correspond to kind of local operators. So this gives me a nice kind of discrete basis that I can use, just polynomials in momentum space. To truncate, I'm just going to restrict myself to polynomials up to a certain degree, or kind of more conceptually, operators up to a given scaling dimension. So I'm specifically going to keep low dimension primary operators in my original CFT of the free scalar. So I just truncate, I have some delta max, I only keep operators up to that threshold. I diagonalize, I can compute the Hamiltonian trivially from just the Fock space expansion of my entries in my Hamiltonian. And then I compute all the entries in H naught and V, I diagonalize, and I look at the resulting eigenstates. And so just to give you some rough intuition of kind of the kind of computational complexity that we're dealing with, the set of states, so the number of states in my basis as a function of delta max grows exponentially. And we're going to be working at delta maxes of roughly kind of 40. So we're going to be keeping roughly 10 to the 4 states. So we're going to have a 10 to the 4 by 10 to the 4 matrix, something I can diagonalize in Mathematica. Yes?
Is it better to use just all the phi squares here? Why not use the massive?
So yeah, so good. So so you're absolutely right. Like, there's no real reason for me to be keeping, or generically, there's no real advantage to keeping squared by squared in V. The reason I'm doing it is because the basis that I'm using was kind of like the motivation for keeping low dimension operators comes from some like the kind of holographic intuition of the decoupling of high dimension operators. And so we just kind of built this like general intuition of low dimension operators and CFTs are a good basis. And so that was the motivation behind this. You could try to find, and there has been a lot of work on finding other choices of bases in like a free massive scalar. So yeah, it's just an intuition of what do I think is a good basis. But yeah, you're absolutely right. There's no intrinsic advantage otherwise to keeping.
Because in TCSA, if you work with massless thing, it has divergence. When you add massive perturbation, the ground energy.
So
issue another of those things.
yeah, good. So there's a similar avatar of this for us, not in this specific example of 2D, But if you look at 2+1T, we don't paper from a few years ago, there is kind of a notion of higher diversity from adding this mass term. It takes to be a bit clever with kind of your choice of basis to compensate for that. But anyway.
But there's no Fergus, sorry, but there was no Fergus.
Ah, true. Yeah, true. Yeah, sorry. Yeah, so yeah, you're right. It's irrelevant for us for two reasons. But yeah, good. Okay. A good question. Okay, great. Let's forget all about how I constructed the basis and everything like that. Just I've handed you a Hamiltonian that approximately describes phi to the fourth theory. Let's diagonalize it. Let's look at its spectrum. So here I'm showing you the mass eigenvalues, which are just the energy squared in the center of mass rank, as a function of the coupling, as a function of the phi to the fourth coupling relative to the bare mass. And so what we see is that kind of in zero coupling, I have a kind of trivial theory where I have the one particle state, the two particle threshold. Because I have a discrete basis, like a finite dimensional basis, I'm approximating the two particle continuum by just this kind of discrete set of two particle states. Then I have a three particle threshold and so on. And then as I increase the coupling, I find that two things happen. One, these curves start deviating from their free theory results, and you can compare it at small coupling to perturbation theory. But eventually the gap closes. And I find that kind of, the 1, 2, and 3 particle thresholds are roughly closing at the same value of the coupling. And as we increase the truncation, we can show that these three kind of intersection points asymptote to the same kind of infinite delta max critical coupling. Yes.
Sorry, maybe you said this, but the mass term.
Yes.
You just set n to 1 or something here.
Yeah, exactly. Everything's in units of n. Exactly. Yeah. Whenever I write G, I mean G over M. Whenever I write mass eigenvalues, I mean M. Yeah, that's right. No, yeah, thanks. I don't think I said that explicitly. So, okay, so this point right here is the critical point described by the 2D Ising model. And we've had some previous work kind of analyzing the vicinity of this region, comparing our results to kind of conformal perturbation theory in the Ising model, but we're not going to talk about that today. Instead, I'm going to ask about these states up here. So, when we diagonalize the Hamiltonian, I get order 10 to the 4th states. So can I learn any interesting physics from these guys up here? And so to do that, or to kind of like start, let's just look at some fixed coupling that's, as generic strong coupling, but not necessarily close to the critical point, because I'm not interested in easing specific things. I just want to study phi to the fourth theory at some finite coupling. And so here, I'm showing you basically the same plot here. So I'm just showing you the kind of all the different eigenvalues. And so what I'm plotting here is I'm plotting the entropy density of these states as a function of their energy density. So this is not at all obvious, and I'm very happy to explain it at the end. But our truncation by setting this kind of maximum delta max or maximum degree for our polynomials kind of puts our states in an effective finite volume. And so we can define a kind of finite energy density we can define the energy density for our states, which is just the energy divided by that volume, and it scales quadratically with the energy. But the punchline is just that these guys, I can compute the finite energy density by dividing the energy by the volume. And so what we see is this nice kind of party growth of our states, which is just a nice sanity check. And so I'm really interested in these states right here. So with low energy density, I find very few states. These are kind of the 1, 2, 3 particle type states. Up here, I find that eventually things start crashing. This is just because of truncation effects. As I increase the truncation, we see the kind of 30 kind of crashes here, 35 crashes a little bit later, 40. So this is a truncation effect. So we want to kind of stay in this regime from roughly 5 or 10 in units of the bare mass up to maybe 50 or 100 or something like that. And so I want to study these states right here. And so one thing we could look at is expectation values. So I'm going to compute the expectation value of a particular operator. It's a combination of d squared phi squared and d phi to the fourth. I've chosen this particular combination because this is a Virasoro primary in the original UV CFT. And so I know that its thermal expectation value in the CFT is 0. And so what I'm plotting here is the average expectation value as a function of the energy density, or equivalently just the energy eigenvalue for different values of delta max. And then I can compare this to the kind of high temperature prediction I would get from conformal perturbation theory. So I have at high energies, at high temperatures, I can think of this as just a free theory kind of deformed by relevant perturbations. So in the infinite temperature limit, this should asymptote to 0. And then I can compute kind of the leading high temperature direction, which is this black dotted line. And what we see is kind of two things. One, at high temperatures or high energy densities, our results agree with this. They eventually deviate at low temperatures, but that's because this conformal perturbation theory approximation breaks down. But also that what happens when I change delta max is roughly, it increases my dynamical range in energy density. The kind of rough value for the expectation value is relatively quickly converge. It's just that I can trust my result, or I get better results over wider and wider ranges of energy density as I increase the truncation. So this is telling me two things. One, it's telling me that my high energy eigenstates appear to satisfy ETH. The expectation value in my energy eigenstates matches that of kind of a finite temperature expectation value. And two, that this kind of averaged information seems to be converging relatively well. Well, yes, absolutely.
Do you know how this plot will look? Is that the average density or the model for perspective temperature?
Yes, good. So the effective temperature is roughly the square root of the energy density. And so I don't have the plot. I don't have the plot generated. I guess. Yeah. What do you want to see that's different? Yeah.
What's kind of limited the expensive heat emerge?
Yeah.
Thermalization goes to zero.
Yeah.
But in other scenarios, when you don't really have the zero, with the thermalization value is a constant divided by temperature.
Ah, good. Yeah.
That would be a violation of pH.
Right.
That
Yeah.
would be consistent with the performance at going to zero.
Right. Right. Yeah. Good. So yeah. So I don't have any plots ready for that, but yes, we've also looked at kind of other non-Virasoro primaries, and yeah, maybe we can talk afterwards, like if you want to see more. But yeah, no, that's a good.
Sorry.
Oh yeah, absolutely. Ah, good. Yeah. So let's jump ahead. Oh, okay. Sorry. I think I have this on a backup slide. So yeah, so this is showing you kind of two different expectation values, and showing that the difference of these two guys is the Virasoro primary, and so this is showing you at delta max of I think 40, the kind of rough spread. So this is showing you the variance. Okay, sorry about that, but no, good question. Okay, great. Another thing we can look at, I just have a few minutes left, so I'll just show maybe like two more plots. So one thing we can look at is the spacing of the eigenvalues to kind of diagnose whether the system is chaotic or not. And so this is showing you the distribution, so the kind of probability of a given spacing between eigenvalues as a function of the eigenvalue spacing. So S is just the separation between adjacent eigenvalues. And so there's kind of two rough things that we want to look for, or two possibilities. So the first is we could get a Poissonian distribution if the system were integrable, or instead we could get this kind of Wigner-Dyson or GOE type distribution if the system is chaotic. And so what we see is that our truncation results agree very, very nicely with the Wigner-Dyson distribution, which is precisely what we expect in a chaotic system. So we see this kind of key feature of this level repulsion, that the odds of any two eigenvalues being the same vanishes. And this is kind of a kind of hallmark of random matrix theory. The other thing we can look at is the eigenvector coefficients. So this plot requires a lot of explanation. So what I'm doing is I'm looking, so each dot on this plot represents a given eigenvector, so a given eigenstate, labeled by its energy eigenvalue or its energy density. So then what I've done is I've computed the overlap of that given eigenstate with my free basis, with my free field theory basis. So that gives me these overlap coefficients C, which is the overlap between my basis and my energy eigenstate. And then I'm just computing what's the distribution of the values of those overlaps. And I can compare that distribution to that, what you would get for just a random matrix, okay? And so this is giving you kind of the cumulative distance. So I just integrate the kind of difference between my distribution that a given eigenstate has and the kind of prediction from random matrix theory. And so 0 would mean that this is literally the same as eigenstates of a random matrix. And far away from this, the max of 2 indicates that it's not random matrix, not eigenstate of a random matrix. At zero coupling, we find that things are very far from a random matrix, as we would expect. We get this kind of nice band structure, which is showing you the different kind of particle number sectors. At weak coupling and at strong coupling, we find kind of roughly the same behavior, which is that at low energies, for these kind of low particle states, these guys are not behaving like that in a random matrix. At very, very high energies, we eventually find truncation effects, which as we vary delta max, just moves to the right. So everything kind of to the right here, you should be ignoring. But that the bulk of the states at high energy, especially at strong coupling, are very, very close to that of random matrix. So we're just seeing kind of more evidence that these states right here, these kind of high energy states, are chaotic. Now, it's hard to tell from this plot, but the bulk of the orange states for this weak coupling, they're also lying in kind of this band here. There's some small kind of order 100 set of states that are deviating. And these states are the kind of potential scar states, these states that have a high, large energy density, but appear to be kind of violating RMT. And if we look at expectation values of operators, we find that those guys are also kind of disagreeing with eigenstate thermalization in the background of these states. And so just last thing, and then I'll be done. We're trying to understand these kind of states here that at weak coupling appear to be not agreeing with random matrix theory and appear to violate ETH. And we're trying to understand what they are. So here I'm plotting the average particle number. And so it's a weak coupling, so there's kind of a well-defined notion of an approximate kind of particle number as a function of the energy density. These two colored populations, those are the ones that were these kind of star-looking type states, these kind of non-RMT type states. And we find that they group into two populations. One are states with low particle number, but high energy. These are exactly the sort of states that I was giving as an example to you on of. These are, basically scattering states. These are states with very small particle number, but just high energy. And so these guys I would not expect to look ETH-like. But these guys right here are states with large particle number, but they're very close to kind of the n particle threshold, which is black dashed line. And so these guys are states with many particles that are all relatively non-relativistic. And so what we're trying to understand now is kind of the extent to which these states, really are violating ETH, and if we can kind of make predictions for their behavior. So, okay, great. Just to summarize, QFTs are chaotic, or at least this one QFT is chaotic, and the expectation is that this should hold for more general ones. The high energy states are governed by kind of eigenstate thermalization hypothesis and random matrix theory. The high energy states that we obtain with truncation numerically appear to be healthy in the sense that their average behavior converges quickly and kind of matches physical expectations. We see kind of evidence of possible ETH violating states near threshold at weak coupling, but at strong coupling, we're finding no evidence for any sort of star-like states in this system. And so in terms of future direction, one kind of thing we're trying to focus on right now is really understand the extent to which these near threshold states truly never thermalize, or if they thermalize very slowly in a way that it's difficult for us to see at some finite truncation, but that as we increase the truncation, we would eventually be able to resolve their kind of thermalization timescales. We're also trying to study kind of signatures of chaos directly in finite volume instead of using this kind of delta max truncation to kind of approximate a finite volume. We'd like to connect these near threshold star states to kind of semi-classical predictions done by Rubikov and Damson. We'd like to kind of further study the predictions of ETH, sort of related to what Tolia was asking about, but also studying, say, off-diagonal matrix elements, not just the diagonal part. We'd like to kind of study higher point functions. So like say a 2-point function in the background of these high energy states. So we can study hydrodynamics. That's down here. We can also compute the spectral form factor, which is kind of another way of studying the kind of distribution of eigenvalues. There's some nice work by Wire and Swingle on how to extract information about hydrodynamics from this. And then finally, we'd like to extend this to kind of other theories. Most notably, say 2D QCD would be kind of the obvious next target, building on the very nice work by Yuan and collaborators, as well as pushing to higher dimensional QFTs. But honestly, you tell me, I think we have a very nice kind of toolkit that I'd like to use to try to understand thermalization more broadly, and any suggestions you guys have of either observables or theories to target, I'd be very happy to hear about. Thank you for your time.
It's spirit of energy.
Yeah.
Much of what you do can be also done for negative G, because it becomes unperturbed and unstable.
Good. Yeah.
Maybe interested to see.
Yeah, so that's something that we've been thinking about doing. So my expectation would be, good. My naive expectation would be that kind of as you increase the truncation, like the way this instability would manifest is that as you increase the truncation, the kind of energy eigenvalues would just kind of keep becoming like increasingly negative. That for any finite truncation, I can only resolve kind of some finite, range in the value of phi. But yeah, it'd be very interesting to understand, things like if I had like a metastable vacuum or something like you know, with like a phi cubed interaction as well, or just turning over the, yeah, this is a very good question. I totally agree. Yeah.
Likely it's gonna be true.
What?
Unlike. Yeah, like. even-
Well, yes and no. Anyway, yeah, we can talk about it after. Yeah. Go ahead. Yeah.
But I also think this way, once you go to negative path, it takes.
Oh, good. Yeah. Good. So this is, so I swept a huge amount under the rug, given time constraints. But yeah, so what we're working in, so yeah, you're asking about what the hell is happening here? Where the energies are going. Yeah. So this is an artifact of the fact that we're working in light cone quantization. So in light cone quantization, the kind of naive free theory vacuum, like the vacuum is trivial in the sense that kind of free theory vacuum doesn't mix with anybody else. And so this is a signature of kind of spontaneous symmetry breaking in light cone quantization. Where here, what I'm really measuring is I'm measuring the difference between kind of energy eigenvalues and the vacuum. And so what this is showing me is that I'm finding some new kind of lowest energy state. And so I should really be interpreting states down here. The lowest state here is like kind of my new vacuum, and then computing energy differences relative to that, if that makes sense. But yeah, no, thanks. Good question. Oh, so.
Are these properties of hydrogen states? The reason why I'm asking is that I think that, you know, we do some truncation, right?
Right.
High energy states, some truncation would not be with approximations to a continuum state, so we would be, you know, like studying that. Should be studying the properties of this particular.
Yes. Absolutely. Yeah, good. So, yeah, that's exactly the right question, which is that, are we just seeing kind of like artifacts of the truncation, or am I actually seeing different things like that? And so that's precisely why, with Kara and Georgia, we're now trying to work with a different truncation. So where we just work in finite volume and use, say, an energy cutoff instead of our cutoff. To try to understand to what extent are we probing kind of features of the truncation versus kind of more unique. Like if I put the system in a bunch of different boxes and I keep seeing the same thing, I would argue that I'm now starting to probe kind of more fundamental information about this rather than properties of the box. But yeah, you're absolutely right. And I think a more general question that I would like to understand is that and this is as somebody who's not an expert on quantum chaos, but lots of the kind of measures of chaos that people use, like eigenvalue spacing and things like this, are kind of inherently finite volume and kind of inherently seem to care a lot about how you discretize, how you truncate it. And it would be nice to understand if there's kind of other more universal features of chaos that are kind of better, more truncation independent ways of trying to. But that's like a more broad question that I really like to answer. But yeah, so the short answer is, I think if you ask questions about the composition of an individual state in this system, like these high energy states, I would say that's highly truncation dependent. I think this average behavior that we're finding, where things are satisfying like the expectation value and things like that, I think those are kind of robust truncation independent. But the only way to really check that is to check both different theories and to check kind of different truncation. And that's what we're trying to do. But yeah, no, you're making a very. Yeah.
Have you computed the integral effect?
Yeah, good. So because the short answer is no, but we would like to. So
That's the basic, that's the part.
exactly. Yeah. So that's one of the reasons why. So for our particular approach of basis of these dimension space students, mapping to the position space, right? But yeah, that's something that we definitely want to have.
I would expect it would be that can be helpful as far.
Yeah, same. Yeah.
But maybe there for.
Exactly. So that's something where that's
The one question is what many people have looked at is just the eating chain.
Right.
You can partition.
right.
And for just the eating chain, you don't see fully.
Yeah, exactly. So yeah, so
When you take two couple eating chain.
Right.
There.
right. No. Yeah, it's a very good question that you're asking. So yeah, one, that's kind of what we're trying to figure out now is kind of what are other good observables for us to look at, like the entanglement entropy, for these states, to kind of confirm whether or not they really are decoupled. My expectation is the same as yours, which is that these guys are not truly decoupled, like, states that are thermalized, but, that are somehow states that thermalize very slowly. And so kind of trying to figure out, which I think is a good question to ask in general, how, given kind of finite computational resources, do I distinguish between those two, but,
I already made this comment, but it's related.
Yeah.
Bigger section of the states. If I understand correctly, the states, they describe massive, very slow particles.
Yeah.
And this is just a diluted gas.
right,
Basic, thing we know about the gases is that it's thermalized. The excuse that it's thermalized slowly doesn't apply here, because we're looking at the eigenstates, they come for infinite time.
that's right, yeah.
So basic question is what happened for the states? I think the goal, because to have a diluted gas, all we need to have thermodynamic physics.
Yeah.
Is large enough.
Right, yeah.
So I do not know if that's the question you're saying that, but I think that I do not know if it's conceivable to do it numerically, but I think the right question is to ask what happens with the states as the volume of the system increases while the density of these particles remains fine.
Exactly. That's exactly what we're trying to answer. But the question is, yeah, how well, or if there's a clever way to try to do that numerically. Yeah, exactly. But that's the difference. Yeah.
The violation of physics.
Yeah.
Underground of physics, slowly move the particles, walks. And we would get right?
Just slow, maybe slowly.
But it doesn't matter how slow, because they're considered eigenstates means that they're working on the infinite temperature. I assume the infinite time, like, right? They're eigenstates, meaning that they're average over. No. Minus infinity. But it's good that they're not very slow, is plausible excuse.
No, good. Sorry. Yeah, so let's, yeah, maybe I wasn't clear in my phrasing. What I'm saying is the following, is that, the states that the eigenstates that I'm looking at right here are eigenstates of this truncated Hamiltonian, which inherently has, kind of an, like a finite resolution in space and time. And so what I'm saying is that, yeah, I'm asking exactly the question that you're asking, which is, how do the eigenstates that I'm finding in my truncated approximation compare to those of the kind of true Hamiltonian in infinite volume? And the question is, are these good proxies for that or not? And so is the fact that I'm finding eigenstates that in this approximation look as if they're not thermalizing, just telling me that I have states that are thermalizing very slowly, but would eventually, to where if I asked for eigenstates of the full Hamiltonian with no truncation error or anything like that, that I would see that they are thermal. That's what I'm trying to distinguish. If that makes sense. Yeah. Well, I'm looking at some kind of like zero momentum type frame, so they can't all be just based on the choice of frame that I'm working in. They can't all be moving in the same direction. They'd have to be slowly moving, but in different. Yeah.
You don't have a activity at the level spacing.
Good. So. Yeah, that's a very good question. So the short answer is yes. And I don't think that that's so. There's two questions you can ask. So let's ignore truncation effects for a second, and let's just ask about like the honest to goodness of it. So right at the critical points right here, this system is not literally the Ising model. He's the Ising model if you look at energies below the coupling scale set by Lambda. And so and of course, if I tune literally to the critical point, there's an infinite set of states below that energy scale because I have no gap. So if I ask questions about, so like, let's say the coupling scale is like, 1 or something like that. If I ask about only those states here, kind of below the coupling scale.
But I thought you put it on the.
Yeah, I'm saying, yeah, good. So yeah, good. I'm saying in the infinite delta max limit, that's equivalent to taking my box to be infinitely large. And so there's plenty of, like, my states are going to be very dense. If I ask questions about kind of that dense spectrum of guys that are still, high energy compared to say 1/r or 1 over the size of the box, then those guys will look not chaotic, they'll look like just the easy model. But then as I go to energies that eventually become comparable to the coupling scale set by lambda, then I'm gonna start seeing exactly the same effects, and I'll find that no, the system should still look generic. Now, we haven't done this, that's just my expectation.
Right, let's think that again.